In stats, we started chapter 7. It's called Sampling Distributions. And what I want to focus on first, before we actually define a sampling distribution, is a parameter and a statistic. So first off, let's review. We have looked at a population mean, a population proportion, and population standard deviation. Those are all parameters. For statistics, those are values based on a sample. We've looked at X bar, P hat, and S. All right, so those statistics are going to create sampling distributions. That's what that definition is talking about right there. So more specifically, this handout is looking at sample proportions and the sample proportion sampling distribution. So let's write a little bit about how well the stat P hat estimates P. So I'm going to scroll down a little bit. We're going to write a little bit down here. If we take one sample the sample proportion P hat, by the way, will probably, it's not a sure thing, be close to the true proportion P. So first off, it's really important to know the difference between P hat and P. P hat is based on a sample, and P is the overall proportion for everyone that we're interested in. A sampling distribution the best way I can think to describe it is we do what I just described many, many times. If we take many, emphasize many, arguably infinite samples of the same size, that means do the process, the same exact process every single time. Over and over again, I want to emphasize that. We do this many times. Then we can create a sampling distribution of sample proportions. Now I have a tiny bit more to say, but I saw a person draw this picture. I don't know if you want to draw it, but maybe it'll help that this sentence right here makes sense. And that is, if I take one sample, then I have one P hat. What if I do this over and over again? Let's make a number line here and plot where they fall on a number line in terms of a proportion. So they're all going to be between 0 and 1, right? So those proportions fall somewhere between 0 and 1. It doesn't have to fall dead center. So it falls between 0 and 1. I take another sample, I get another sample proportion. I do it again, I get another one. I do it again. What if I get one like way out here? It's like out of control. But I do this many, many times. So slowly, these P hats are going to start to pile up. and create a bell shape. Now that's based on the fact that I have a large enough sample. So I really need to have a large sample. But if I had enough time, I'd make a nice looking bell curve out of all these p hats. And I'm out of room at the top there. But imagine that I spend a long time and I have all these p hats. So like so many samples. In theory, the largest possible number of samples from our population creates a monstrous stack of p hats. That is a sampling distribution. Let me write this on the side. Sampling distribution. Now, the whole purpose of this is actually something really unique, because if I only do this first sentence right here, my sample is going to be off. It's not going to be perfect. But we can compare it to the sampling distribution. And Gauss and some other statisticians had a very clever idea. What if I take the mean of all these p hats? The mean of the p hats will actually equal the true proportion. Let me write that out in words. The mean of all the sample proportions, these are hypothetical, by the way, will be equal to the true proportion. Now, we know a little bit more information than that, and that's what the next few pages are about, but that just gets us started. That purple sentence about sampling distribution is where many people just get lost. This chapter is very short, and we have some weird definitions, but if you can master what I wrote where it says sampling distribution, then you'll be just fine this chapter. We went a little further on Friday, and we practiced identifying the parts of these studies. So we identified the population, parameter, sample, and stat. So maybe hit pause and do it and see if they match what I get. So our population of interest on that first example is all residential telephone numbers in a large city. The sample, let's skip parameter for a second. The sample is 100 of those telephone numbers. All right, the parameter, we're talking about proportions. You see the percentage there? Like, look at the example down below. That's about means. This one is about proportions. So the parameter is just plain old P. Let's rewrite that. True proportion. Of unlisted telephone numbers. And in this case, it was 52. Supposedly. Statistic, we're talking about p hat, sample proportion, of those numbers. I'm going to say unlisted. That's important. And we know it is p hat equal to 0.48. All right, let's try one more. This one kind of bugs me because, I don't know, I should have typed it better. Because they're sampling female college students, and our population is all adult American women. But you could have someone from another country going to the college. They're not necessarily American, so I don't know. That I should have worded this better. But this is all, we're looking at all adult American women. And our sample, they don't tell us how large. So sample of female college students. What I am more worried about is the parameter and the statistic. So we are looking at mu, the true mean, height of adult American women. And they told it to us. We know it is 63 inches. For the statistic, we're talking about X bar. It is 64.5. Sample mean of female college students. All right, that's as far as we got today. You have a good weekend. Bye.